the periodic table. Now, they call this a periodic table because in chemistry class, you periodically have to look up at it. But there are regular periods. And these guys down here, the actinides, these are the really fun, energetic. Most of these things don't exist without a lot of significant effort to get them there. But this one right here, uranium, does exist. All nuclear reactors, virtually all nuclear reactors use uranium. All civilian nuclear reactors in the world use uranium. And all civilian nuclear reactors produce plutonium. It's just physics. Some level of plutonium is going to be produced. So what do we do about that is sort of the question. And I like Nick's approach. And that's a distributed network, sort of not living off the grid, sorry, but living on a better grid. And I keep trying to coin terms. You know, don't you want to be the guy that decides, you know, like cyberspace? I mean, what a great term. So I keep trying to come up with something. And this week, it's total planetary impact. It sounds very Star Trek. I don't think I'll get there. But about 20% of our electricity in the US is produced by, depending on who you ask, 104 nuclear reactors. Where's one of my, yeah, there, I'm getting a nod from my chief nuclear officer. By the way, I don't, you know, design nuclear reactors. I hire people that do that. Mega power is the large reactors, large coal plants, large gas plants, large PV plants, massive, huge projects and undertakings, relying on the economies of scale instead of the economies of mass production. They're suited for large population centers, except you can't really build them in a population center. You've got to build them far away, and you've got to ship that electricity. And if you know anything about electrons, those things are kind of have a free will of their own. They kind of wander around wherever they want to, so you get loss of transmission. You pay about $1 million a kilometer just for the wire to move it around. So there's a real approach about grid-based electric production. And that's what we refer to as a different way. So Hyperion was formed several years ago through the efforts of Los Alamos Labs, Altera Group, which is a venture capital firm based here in Denver that invests heavily and exclusively into energy projects and energy technology. This is not the actual reactor. It's actually a cross-section. If it was a reactor, fuel would spill out on the ground. But the idea is this thing's about this big. It's about, you know, 2 meters around and a couple meters tall. It's small, and it'll run about 20,000 US-style homes, or as we like to say, 100,000 homes anywhere else. This is a full plant. This thing is sort of 1/4 of an acre. Now, contrary to what you've heard on CNN, if you actually caught this, for a while there, people called this the hot tub reactor, and then people immediately, because it's about the size of a hot tub, two hot tubs stacked on top of each other, and then people immediately on the media, because they're so accurate, they picked up that we were going to put a nuclear reactor in your backyard. So we actually have, I think, 800 consumer calls for their own nuclear reactor. And these things cost about $50 million. So if there's anybody in the audience that wants their own reactor, I can sell you one. I'm just thinking maybe you should probably join up with some other people in the neighborhood. The attributes of our reactor are, it's got to fit on the back of a flatbed truck. Remember we talked about Africa and developing economies? If it fits on the back of a flatbed truck, we can take it anywhere. We can put it on a train. It's the right size. That actually became the one factor that dictated all of the science, is we've got to put this on the back of a flatbed truck. It can't have internal serviceable parts. It's got to be this battery metaphor. You've got to be able to do this, because our proposition is to take nuclear power into places that it hasn't been yet, either because they don't have an infrastructure for it, because they didn't have a need for very large plants, or because they weren't in sort of an economic basis in order to be able to afford a plant. We've got to keep it below 20% enrichment. I love Bob's so cute. Bob, Amy, commercial plants are 3 to 5%. They are. Commercial plants are 3 to 5% enriched. But they're, enormous. So the only way that you're going to get a small plant to work is by enriching it a little bit higher. And so it's less than 20%. And it operates at about 500 degrees Celsius. And I guess degrees Celsius is somewhat redundant, but that's pretty hot. That's mathematicians, 900 degrees Fahrenheit. So that's pretty hot coming out the other end. And it's hot enough to create a steam cycle, to turn a turbine, to run a generator, to make electricity. Or you could take that steam and use it for doing more efficient mining. It's got to be self-regulating in a way that we haven't seen before, which means there's no Homer involved. You know what I mean? You know, we're still got to have the computer and the dog and the guy, but hopefully no Homer Simpson sort of, you know, thing where he's got a fuel rod or something. When I talk about this project literally every week, and the metaphor, the phrase that I use is you can't pull a Homer. You can't do that with our reactor. If you can pull a Homer, then we're not going to make it as a company, because that's the big fear. It's Homer Simpson. And we've got to close our own fuel waste cycle. We're taking responsibility as a company. Hyperion Power is taking responsibility for our fuel waste cycle. Now in the US, we're not allowed to take responsibility for our own fuel cycle, but in most every other country in the world, we can. We can work within their construct, their policy, their waste disposal, their recycling policy. So we're talking about a different way, again, of approaching nuclear energy. And of course, no reactor can blow up atomically. That's I guess, okay, so the theoretical physicist in the back is going to say, yes, yeah, it could. But there's also gravity-free days too. Based on what we know, there's no way for it to blow up atomically. Our reactor is designed so it can't melt down. And people misunderstand how nuclear reactors work. Most reactor incidents, as they like to call them, I love these terms I've been exposed to in the last 3 years. Most reactor incidents involve human error and the steam cycle. It has nothing to do with the nuclear part of the plant. So by separating out the nuclear part of the plant, which is what we've done, and keeping that away from the steam cycle, we've got a very self-contained, very energetic way to boil water, create steam, turn a turbine, which goes into a generator, and makes electricity. So those are our key criteria. And these, we actually came up with these several years ago. And when Pete Peterson was working on this project as long as almost 13 years ago, he had these in his mind. This key set, though, was developed by going out to the marketplace and asking them what we want. And we've got, I think today the current count is customer commitments for about 133 of these units around the world. So we know that the market does want this, they want to be able to generate baseload power in a grid basis or a grid appropriate fashion. The reactor itself puts out about 27 megawatts of electricity. Today we had the big argument about whether or not we should be talking about thermal. Maybe people don't care about thermal. You know who cares about thermal? The guys that are making steam for oil sands, oil shale projects. And this reactor will last from 5 to 10 years depending on use. Sort of you get a little piece of paper that says, depending on use, your results may vary. Each unit costs between 30 and 40 million bucks. That works out to be about $5 a million BTU. And I'm using two different, I'm using a capital cost for a reactor. I'm not including the whole plant. But the $5 a million BTU for generating, generating heat or process heat or electricity is pretty good. It compares with the dirty sort of carbon basis of generating that kind of energy. Our commitment is to be able to generate electricity anywhere in the world for less than 10 cents a kilowatt hour. What do you guys pay today? Anybody know? This is the audience to ask. 6.2. Where the hell do you live? Are you off the grid? Oh, Longmont. Good for Longmont, because it's about 8.2 downtown Denver. At least that's what I pay.
Well, wholesale or retail is an important thing you're talking about here. Wholesale.
No, I'm talking about retail, including operating cost and cost of capital and the whole thing over the life of the plant. That's our commitment.